Hello friends, welcome to the Arpit course on numerical methods in civil engineering. I am Yogesh Desai from Department of Civil Engineering, IIT Bombay. This Arpit course is being planned to be delivered in a modular fashion consisting of 5 modules, and today's lecture is concerned with module 2, solution of equations and numerical approximation, and the topic for today's lecture is numerical differentiation in two-dimensional domain, and after that we will talk about numerical integration. So, in the previous lecture of this module, we talked about numerical differentiation as applied to one-dimensional domain. So, now we will talk about numerical differentiation in two-dimensional domain. Let us start with simple equation, Laplace equation, which can be used to study steady state heat conduction without source or sink within the domain, del square T by del x square plus del square T by del y square equal to 0. This is also known as harmonic equation. This equation we could have also used to study steady state seepage through porous media. We could have also employed this equation to study torsion of non-circular cross section staff. So, if this Laplace equation we apply at point I j in the domain as shown here, and let us consider step length h uniform both in the x and y direction, we can express del square T by del x square using central divided difference expression. Similarly, del square T by del y square also we can express in terms of central divided difference, and that is what we have done here. Okay, so, we get values of function t at these 5 points as we see here. They appear in this expression. So, what we do? Something similar to what we have been doing in chemistry, molecular structure. So, I talk about finite difference molecule. So, this molecule we apply at all the points in the domain where the differential equation is written down. So, this aspect will be covered at length in module 4. So, right now my aim is to explain how these expressions have been derived. Okay. So, this finite difference molecule we can apply at all the points. As a result, we will get simultaneous algebraic equations, and these algebraic equations we solve to get the value of the continuous function at the select point. And if required at any other point, we can work out the value using concepts that we studied in the topic interpolation. So, that is what makes the complete package. Different concepts covered in different places now put to use to solve a given differential equation. So, what we discussed earlier was second order differential equation. Now, I talk about fourth order partial differential equation. This equation we encounter in plate bending in the absence of shear deformation effects. Operator del 4 is known as biharmonic operator, del 4 by del x 4 plus 2 del 4 by del x square del y square plus del 4 by del y 4. We apply this operator, central difference operator, to the given differential equation, and as a result we get this del square by del x square. When we are applying the operators at I j, we get del square w I j by del x square plus twice del square by del y square of del square w I j by del x square plus del square by del y square del square w I j by del y square equal to q by d, and we need the value of function at 13 points in order to construct such equations. So, let us look at one term at a time. I am looking at the fourth derivative with respect to x, and we studied this when we discussed numerical differentiation in one dimensional domain. We get now these 5 terms, and in terms of the value of function at these 5 terms, 5 points, we get this fourth order derivative. Similarly, similar to what we did earlier, I can show it in a graphical form, so that just this fellow we can slide around the domain to get the fourth derivative at different points in the domain. So, this was del 4 w by del x 4. Similarly, we can talk about del 4 w by del x square del y square, and all these function evaluations will come into play, and in the molecular form at 9 points we work out the value of function, and in terms of these coefficients we are able to represent this fourth derivative. Similarly, fourth derivative with respect to y. So, what we saw in the x, now similar coefficients we see in the y direction, and putting all these terms together, now we get our finite difference molecule to be applied at all the points that we select in the domain, construct simultaneous equations and solve these simultaneous equations, and that is what we do in finite difference method. So, as I talked earlier, at 13 points we need to evaluate the function, and in terms of that we are able to express this biharmonic operator. Likewise, if I want third derivative, del cube f by del x del y square, we do differentiation in one direction at a time. So, first I do differentiation with respect to y, and then with respect to each of these terms we do differentiation with respect to x, and that is how we got this expression over here. And in the finite difference molecular form we get expression like this. Now, in all this differentiation, as we discuss in the case of one dimensional differentiation, when you add all the coefficients, they should add to 0. So, in any such expressions you see the summation of these coefficients will be 0. And the reason is, in our pursuit of deriving expressions with more accuracy, the simplest possible case, derivatives of constant valued functions, all derivatives have to be 0. So, this aspect would be captured if and only if all the coefficients add to 0. Okay. So, this you must verify whenever you deal with numerical differentiation. So, let us talk about numerical integration. In many engineering applications, we need integrations of type I equal to integration f x dx, or I equal to double integration f x y dx dy, or triple integration f x y z dx dy dz. Numerical techniques are often employed for computation of these quantities, and such expressions we encounter typically in a finite element formulation. So, if you try to visualize this, the first fellow here is area between a given curve and your x axis for the given parameter range. The second expression, double integration, is a volume beneath a surface. If you talk about triple integration of this form, basically we go in the hyperspace, we cannot visualize this, but the first two fellows we can try to visualize and see how best we can integrate these expressions. So, let us start with integration in one dimensional domain. Consider that we are asked to evaluate integration from a to b f x dx as shown in this sketch here. As I mentioned, we want area beneath this curve and bound between the curve and the x axis for the parameter x equal to a to x equal to b. If the integrand f x is a simple continuous function in x, the integration can be evaluated analytically. We can do it by hand. Alternatively, the integrand can be computed by employing numerical techniques like trapezoidal rule, Simpson rule, etc., that you would have studied earlier. Depending upon how the function varies, a single trapezoid may be enough, or simple Simpson rule applied over the entire domain may be adequate. If the function varies rapidly, then we can consider splitting the domain into subdomains, and over each of these subdomain we can apply such expressions. Many times, especially when we are doing everything numerically, we may not know the explicit nature of the integrand. So, in such cases, the computation becomes bit challenging. So, let us see how do we proceed. If we use trapezoidal rule and we take single trapezoid, then the hatch region as shown here would contribute to error. That much area we could not account for properly in our computation. So, this is our trapezoidal rule giving this much error if this was the function. I approximately given by b minus a by 2 into f a plus f b. We could have rewritten this expression as I approximately equal to W 1 f a plus W 2 f b, where W 1, W 2 are weights, each b minus a by 2. Okay. So, this is the trapezoidal rule we all are familiar with. Rather than discarding such simple expressions outright on the basis that we may get large errors like this, many scientists, mathematicians in the past, they have worked with very simple equations, applying them in a different way, such that instead of getting huge error, we get excellent numerical results void of any error. So, this has been the approach undertaken by large number of mathematicians and scientists in the past. In order to make the application of numerical method more expeditiously over a range of problems, what is done is we convert the physical space to an equivalent mathematical space using natural or intrinsic coordinates xi, for example, as shown here. And how that is done? By doing coordinate transformation. We assume for x value E xi plus g, and we know that at xi equal to minus 1, x has to be a, at xi equal to plus 1, x has to be plus b, and from that using essentially Lagrange first degree interpolating polynomial, we work out expression for x in terms of xi, and that is what we substitute in the given equation, perform the differentiation, and we get the relation between dx and dxi in terms of determinant of matrix J times dxi, where determinant of matrix J is called Jacobian matrix of the coordinate transformation, which for this line integration is simply b minus a by 2. Okay. So, with this we have converted our given integration in our physical space x to an equivalent mathematical space, always ranging from minus 1 to plus 1. regardless of the size, shape, orientation of our physical domain, we work with an equivalent transformed mathematical domain ranging from -1 to +1, as we have seen in this expression. So, now we are going to work with the expression -1 to 1 capital F xi d xi. So, this capital F xi has absorbed this determinant value of Jacobi in our integrand expression. So, that is nothing but F xi, which is obtained by substituting for x the equivalent expression in xi times determinant of Jacobi. So, that is our capital F xi. So, what we have done? Our physical space we have transformed to equivalent mathematical space in natural coordinate -1 to +1. So, what Gauss did? He worked with trapezoidal rule, but applied it in a different way. Our usual trapezoid is constructed taking the end points of the region. Instead, Gauss constructed the trapezoid by taking two points inside the domain. These points, let us say, are C and D, and in terms of value of function at C and D, he constructed the trapezoid by extending the straight line joining F C and F D to the end points. Now, look at the beautiful simple thing that he has done. He says, by doing so, I have areas A1 and A3, which are overestimated compared to the actual area beneath the curve. On the other hand, I have part of the area which could not be accounted for. For some certain type of integrand, if I am able to find uniquely these points C and D and the associated weights W1, W2 such that A2 becomes A1 plus A3, area under the curve from xi equal to -1 to +1, and the area of the trapezoid thus constructed will be the same. What does it mean? We have integration void of any error. Isn't it a beautiful concept? Yes, the concept is beautiful, but we cannot apply to any type of integrand and say that we are getting integration done numerically without any error. Specific type of integrand, yes, we can work out where the C and D should be and what should be the W1 and W2, the associated weights. So, now the question is, we have 2 plus 2, 4 parameters W1, W2, locations of point C and D. So, we need to find these 4 quantities uniquely for a given type of integrand. So, let us go one step backward. We talked at length linear interpolating polynomials, correct? In finite element method, where we encounter numerical integration extensively, again there we deal with interpolating polynomials. So, keeping this in mind, Gauss thought, let me talk about integrand which is a polynomial. Now, since I am dealing with 4 quantities to be determined uniquely, what kind of polynomial will have 4 terms? And the answer is obvious, it is the cubic polynomial, because it has 4 parameters A0, A1, A2, A3. So, he considered integrand to be a cubic polynomial. This is such a simple equation, we can evaluate it analytically, and the analytical value is 2 A0 plus 2 by 3 A2, and also we have the numerically computed value of the same as W1 capital F at C plus W2 capital F at D. and we put this fellow, the f c and f d, we take the expression for f xi and substitute for xi c and d, we get numerically computed value as given in this equation. Now, in this numerically computed value and the analytical expression, we compare the coefficients of a 0, a 1, a 2 and a 3. As a result, we get 4 algebraic equations. We notice that these equations, some of them are nonlinear. If we can solve these 4 equations in 4 unknowns uniquely, we have solved the problem. What then we would have achieved? Numerical integration done for integrand to be cubic polynomial, and this numerically integrated value has 0 error. So, this is the beauty of the concept. So, now let us see whether we are able to find C, D, W1, W2 uniquely from these 4 fellows. Let us look at equation 2. It gives us W1C equal to minus W2D. Let us substitute this fellow into equation 4, and from that we get W2D times D square minus C square equal to 0. Now, this term gives us 3 possibilities, either W2 equal to 0 or D equal to 0 or D square minus C square equal to 0. W2 cannot be 0. In that case, we are getting contribution from only one point. So, then we are not talking about trapezoid, and by the same logic D also cannot be 0. So, we are left with only one choice, D equal to plus or minus C. Now, again if D equal to plus C, we are coming back to one point. So, this expression gives us only one unique acceptable condition, that is D equal to minus C. Okay? Now, if I put this fellow back into our equation 2, we get W1 equal to W2, and that when we substitute into equation 1, we get W1 equal to W2 equal to 1. So, this fellow let us put in equation 3 with C square equal to D square. As a result, we get unique location of these points, minus 1 over square root 3 and 1 over square root 3. So, what have we achieved? If we find value of integrand at 2 specific points in the domain, one is minus 1 over square root 3, other one is at plus 1 over square root 3, simply add the value of this function at these 2 points, and the end result we get exact value of integration, no error. Isn't it a fantastic approach? Because of the simplicity, elegance, robustness of this approach, it is being used widely in numerical computations and in finite element method in particular. Exact integration if integrand is a polynomial of degree 3 or less, because that was our starting point on the basis of which we derived this equation. Okay. So, extending the concept, we can talk about endpoint Gauss rule. Points where we sample the function in terms of which we work out the value of the integration. In honor of scientist Gauss, they are known as Gauss points and the expression as Gauss rule. So, if we talk about endpoint Gauss rules, we take endpoints in the domain from minus 1 to plus 1 and we work out the values, unique values of the Gauss points xi I and associated weights w I. We can then tabularize all these values and use them in our calculations. So, we have given in this tabular form, and this table has been taken from reference Desai Y.M., Aldo T.I., Shah H.H., that is our book on finite element method with applications in engineering. 1 over square root 3 is this fellow over here, 0.57735, etc. If you talk about 3 Gauss points, 0.77459, etc. is nothing but square root 0.6. So, these values are very easy to remember. We find the value of function at these specific points in our normalized domain and multiply it by the associated weights, and we have very nice elegant expression for doing integration numerically. Please note, if we employ n point Gauss rule, it will give exact value of integration if integrand is a polynomial of degree 2n minus 1 or less. Now, this is a very important thing. If I know the degree of polynomial that is there in the integrand, looking at that we can work out how many Gauss points n we need, so that we get exact value of integration. Other thing that you would like to note is summation w I has to be equal to 2. If you are given a constant valued function, all epsilon i's are constant, and if I integrate minus 1 to 1 constant value d xi, that integration will be 2 c. So, in order to get the numerically correct value, since all epsilon i's are the constant c, summation w I has to be 2. So, this we have to observe in this table. So, that is the reason why you take only one Gauss point, the weight is 2. When you take 2 Gauss points, w 1 is 1, w 2 is also 1. So, w 1 plus w 2 is 1. Similarly, just I give one more example, number of Gauss points equal to 3, 2 of them have weights 5 by 9. So, 5 by 9 into 2 plus 8 by 9 is again 2. So, summation w I is always 2. So, please remember this. Let us look at application of this numerical integration that we just discussed. I want to integrate this 5th degree polynomial here. So, that is our integrand using 1, 2 and 3 Gauss points. Tell me, just looking at this, how many Gauss points we need in order to do the integration without any error. 2n minus 1, you set it to 5, that gives me value of n as 3. So, when we take n equal to 3 or more, we will have numerically obtained value void of any error. Whereas, when I use points 1 and 2, since we will not be able to go up to the 5th power term, our expressions numerically thus obtained will have some error. Okay? Since this is a very simple integrand, we can work it out analytically, and that value is 39,600. Then what we do? Using coordinate transformation, we convert this fellow in terms of xi ranging from minus 1 to plus 1. So, this is what we have done. Again, Lagrange interpolating polynomial, and we have expression for x in terms of xi, and also dx equal to 2.5 times d xi. Substitute these fellows in our equation here, and we have then equation I equal to minus 1 to 1 capital F xi d xi to be evaluated using 1, 2 and 3 Gauss points. In this expression, put xi equal to 0, w I is 2. So, we get approximate value of this integration when done numerically is 8787.50, very bad compared to the exact value. And why is that? When you take one Gauss point, 2 into 1 minus 1 equal to 1, it will give you exact value of integration if integrand is a polynomial of degree 1 or less. So, that is the reason why this fellow gives large error. Similarly, if I do 2-point Gauss rule computation, again the value is less than the actual value 36,822. This fellow would have given exact value had our integrand been polynomial of degree 3 or less. And if you use 3 or more number of Gauss points, now you will recover the exact value. Okay? So, this is how we do numerical integration in one dimensional domain. In order to have some practice, let us talk about assignment. So, this assignment, the first question deals with numerical differentiation in two dimensional space. So, given continuously varying function t in x y, find out del square t, del 4 t and del cube t by del x del y square at point 4 phi. Use step length h equal to 0.05. Well, we have discussed all these expressions. We have finite difference molecules for these expressions. Just work out these numerical values. Okay, it is very simple, straightforward problem. Question 2 pertains to numerical integration. A and B are straightforward. You have to convert first of all these expressions in terms of transform space from -1 to +1 and do the integration. You can easily guess that the solution for part A, if you use 3 or more number of Gauss points, you will get exact value of integration. Okay. The second one, in order to estimate how many Gauss points you need to go back to our discussion on curve fitting. Over this tiny range, try to express this function in terms of low degree polynomial and see which degree polynomial gives you the best fit to this continuous function. So, just I am telling you, if you want to guess how many points are required, that is the approach you would like to take. Since the integrand is not a polynomial to begin with, the numerical integration unfortunately will have some error. But if you take more number of terms to represent this given integrand in its equivalent polynomial form, you can bring down the error in computation. Okay. Question 3, that is part C, is interesting. You see, we have range 0 to infinity. Now, this we have to transform to finite domain -1 to +1. So, somewhere we will have to put artificial boundary. Now, where to put this boundary? How to do this integration numerically such that we do not have large error in our computation. For that, you will be required to do some numerical experimentation. Notice we have term here e raised to minus y exponentially decaying function. Okay. Split your domain into 2-3 parts and then you do your numerical integration for these different parts. The last part, because e raised to minus y, it has already decayed so much, there you can say take some arbitrary boundary at some distance, and the other 2 parts or so you can work out the actual transformation, perform the numerical integration for these different parts you have taken, take 1 part, 2 parts, 3 parts, so on and so forth, and see how best you can get the numerical answer which would have less error. So, there will be some numerical experimentation as I mentioned, but when you do this exercise you will have better idea as to how we perform numerical integration. Okay. So, with this we stop for the time being. Thank you.